distribution of grades, I would say. Okay. I'm a little behind, so I'm going to move forward with things. I want to spend a little bit of time today. I'm going to finish up talking about redox and so forth. Then I'm going to come back and talk about energy, as I said, and then we'll dive into talking about the carbohydrates. So a lot of things on tap for today. So last time I was talking about the sort of basic terms that we have, catabolism, anabolism, and I'm not sure if I said it or not, but basically the word metabolism is the sum of catabolism and anabolism. So metabolism encompasses everything, catabolism encompassing one component, anabolism comprising another component, and that's the overall thing. It's metabolism that many people associate with the biochemistry of biochemistry, or the chemistry of biochemistry. All right? Last time I finished with this scheme right here showing you what I described as oxidation reduction, or what we more commonly abbreviate as redox. I pointed out that oxidation always involves a loss of electrons. Reduction always involves a gain of electrons. In a biological system, it's a little bit more confusing than that because we have electron carriers. So electrons, as I said yesterday, are not released freely into the environment because that would be extraordinarily reactive. And they would react and cause reactions for every molecule inside the cell that they happen to encounter, and that would be very deadly for cells. So cells have electron carriers that accept electrons when oxidation occurs, or that donate electrons when reduction occurs. Okay? So there are three carriers that we talk about primarily. The first of these is called NAD. It's got a longer name than that, but essentially everybody calls it NAD. And NAD is shown in the oxidized form on the left. That means it has not yet gained electrons. And the reduced form is shown on the right. It has gained electrons. And what's the difference between these two? Well, if you look in this ring structure up here, you can see essentially a benzene ring here. And over here, you can see that's been altered by the addition of electrons. So that's the difference between the two. The reduced form is known as NADH. The oxidized form is known as NAD. Okay? In fact, NAD is actually NAD+. And so the question is, well, I go from an NAD+ to an NADH with a charge of 0. How does that happen? I've added a proton, right? Well, a proton we know has a charge of +1. So if I've gone from a +1 to an add a proton and I've gone to a 0, that must mean I've added also 2 electrons. So +1 + 1 - 2 equals 0. So NADH has a charge of 0. NAD has a charge of +1. Another carrier that we talk about, we'll talk about it more when we talk about photosynthesis, is called NADP. It has the identical structure of these guys, NADP on the left, NADPH on the right, except for there's a phosphate down here. And again, we're not going to worry about the structures of these, so this isn't really critical for our purposes. Okay. Another electron carrier that we have is FAD. And FAD exists in an oxidized form known as FAD with a charge of 0. And FADH2, which also has a charge of 0. And again, it's picked up 2 protons, and it's picked up 2 electrons. So it's gone from a 0 to a 0. The oxidized form is on the left, no electrons. Reduced form on the right has picked up those 2 electrons. Okay. Now, more of the same thing. We don't need to worry about that. If we look at the reactions that are involved in making NADH and NAD, we can see, for example, over here, if we had this reaction here, what would this look like inside of a biological cell? Well, this reaction is what would occur chemically, but I said that we don't have electrons released freely into the environment. So if this reaction were occurring in the cell, here's what it would look like. It would have on the left ethanol. Okay. It would have on the left plus NAD. because NAD plus could accept electrons. All right? On the right, it would have acetaldehyde, and instead of having this, it would have NADH plus one extra proton, because only one proton goes into NAD. Now, look at what's happened. I start with an oxidized form of NAD on the left and a reduced form of ethanol. On the right, I end up with the oxidized form, which is known as acetaldehyde, and a reduced form of NAD, which would be known as NADH. So they basically swapped electrons and protons. That's what they've done. Okay? So one thing got reduced. NAD got reduced to NADH. One thing got oxidized. Ethanol got oxidized to acetaldehyde. So that's why I say for every oxidation, there is a reduction. The electrons are going from ethanol to NAD, producing acetaldehyde and NADH. That will be true for every oxidation reduction that we will see inside of cells. Every single one will occur like that, whether it's NAD or it's FAD in some cases, as we will see, or if it's NADP. In every case, we will have an electron acceptor that will accept those electrons. Now, you might say, well, how do I know if it's an oxidation reduction? Well, it turns out it's simpler than that, because anytime you see NAD or FAD or NADP in a reaction, it's there because it's accepting electrons. So you will know it's a redox reaction anytime you see an electron carrier in a reaction. You will know it's an oxidation reduction reaction anytime you see an electron carrier in a reaction. And I will point these out to you as we go along. Okay. So that's what those guys look like. Another thing we talk about relevant to energy, and by the way, redox reactions are involved in energy because oxidation generally releases energy. That's why lighting a match the match is hot, because it's releasing energy. That match is getting oxidized in that process. So oxidation reactions will generally release a fair amount of energy. Well, that energy in the cell is not stored as heat, although we will find places where heat is, in fact, saved. Okay? But instead, the reactions, the energy of the cell is stored in high-energy phosphates. I've mentioned that ATP is the gasoline of the cell, meaning that it's the energy that makes the cell go and do the things that cells need to do. It's useful for us then to look at the structure of ATP and understand the sort of energy component relating to ATP. All right? If we look at this guy here, we see a sugar, we see a base, and we see 3 phosphates. Okay? Those 3 phosphates are each negatively charged. Bang, bang, bang. And those negative charges repel each other. However, they're held very close together. If you take a north pole of a magnet and you put another north pole of a magnet here and you try to put them together, they resist that, right? They don't want to be held close together, and the more you try to hold them closer together, the more they resist it, right? The same is true of these phosphates. These phosphates really don't want to be next to each other, but they're stuck next to each other because there's a covalent bond that links them. If we break that covalent bond, 2 things happen. 1, the phosphate is happy to leave. And 2, energy is released. So converting ATP to ADP releases energy. That is why ATP is the gasoline of cells. That's the reason ATP is the gasoline of cells, because we can think of this thing as having a lot of potential energy. The energy is realized and released when we break that bond, and that phosphate goes flying away. Make sense? I see some nods. Okay. So that's good to know. ATP, ADP, AMP. Right? The most energy is contained in ATP. Let's see. This shows a variety of phosphates. There are some things that have phosphate that actually have more energy than ATP does. We'll talk about them when we get talking about metabolism. But I just show these to you here. These are showing delta G0 prime values. I'm going to describe those to you in a minute. But this guy up here, phosphoenol pyruvate, you can see has about twice as much energy as ATP does. Okay? About twice as much energy as ATP. So some of these things have a lot of energy stored within them. And that turns out to be important inside of cells. Okay. I like to show this figure because it sort of summarizes all the things that I showed you yesterday. That summary includes the fact that if we think about what is happening inside of cells, cells are burning molecules that have high energy. That releases energy. So we burn glucose, for example. When we burn glucose, we release energy. That's an oxidative process. And the energy of that oxidation is captured in the form of ATP. ATP is then available whenever cells need to do something, whether it's making molecules, whether it's running and jumping, whether it's thinking, whether it's seeing. Your eyes, you actually use a fair amount of ATP. People that go on fasts for long periods of time go blind. They lose their energy necessary to maintain their eyes. Okay? There's a surprising statistic that whenever I say it, I marvel at it. Okay? And it's a little hard to believe, but it's true. And the statistic is this. You make and break down every day your body's weight in ATP. You make and break down your body's weight in ATP. That tells you how much ATP you're going through. Okay? That's, I don't want to say a ton because, well, that would suggest I'm heavier than I am, but that's a lot of ATP. Okay? So that's important to keep in mind. The body is having to make and break down a lot of that stuff in a given day, and that's pretty cool. Okay. Well, the last thing I want to talk about on this slide is the actual energy itself. Okay? So how many liked going through Gibbs free energy when you had freshman chemistry? I don't see any hands. I see one hand. Okay, you like that? Okay, well, all right. So most people didn't like that. All right? So I try to keep energy at a fairly basic level, not because I want to be popular, but because I think the more that you absorb of something, the less complicated it is, the more likely you are to understand it. All right? Gibbs free energy is a very important entity. It's a very important thing for us to understand. Okay? Gibbs free energy. What is the importance of Gibbs free energy? Gibbs free energy tells us the useful amount of energy that a cell has to do things. The change in the Gibbs free energy for a reaction, and by the way, we measure Gibbs free energy associated with reactions because reactions always involve some component of energy. You want to underline something, underline that. All reactions involve some component or some consideration of energy. Gibbs free energy turns out to be a very useful kind of energy for us to understand, because if we can understand the Gibbs free energy of a reaction, we can understand the reaction and the direction of a reaction. And that turns out to be really important as we're studying metabolism. Okay? So, there's an equation up there. Let's not work with the equation to start. Let's talk about what you remember about Gibbs free energy from freshman chemistry. And now I have a complete blank on your face. Joke. All right. So, there's three things that we teach to start about Gibbs for the change. It's called the change in Gibbs free energy, or the delta G. Okay? The delta G value is the measure of the change in Gibbs free energy for a given reaction. Delta G. Okay? If I know the delta G for a reaction, it enables me to tell the direction of a reaction. So if I know the delta G for a reaction of A going to B is minus 5 kilojoules per mole, If I know that that value is negative, I know that that reaction will go forwards. A will go to B. If I know that the delta G for that reaction is positive, let's say it's plus 10, I know that that reaction will move backwards. B will go to A. Okay? And I know that if the value of the delta G for that reaction is 0, that reaction is at what we call equilibrium. Now, one of the messages that chemistry is not very good at communicating to our students is that equilibrium does not mean equal amounts of A and B. It does not mean that. Okay? Very big misconception. And half of you on the exam are going to try to tell me it means that. It doesn't. Okay? What it means is, what equilibrium means is that the ratio of A and B is not changing. It's staying constant. Okay? That's what equilibrium means. And it's the ratio of A and B that actually is critical for me to understand whether a reaction is going forwards or a reaction is going backwards. Let's think about this. Now I bring up the equation. Delta G is equal to delta G0 prime. That's a different kind of delta G I'll talk about in a minute. Plus the gas constant R times the temperature in Kelvin times the natural log of what I call products over reactants. So if I had A goes to B, the product would be B, and the reactant would be A. Okay? There's two things up there that say delta G. Right? The delta G for the reaction that I'm talking about is the very first one, delta G by itself. What's the other one? What's the delta G0 prime? The delta G0 prime is the delta G under standard conditions. You guys studied the gas laws in freshman chemistry, and you had standard temperature and pressure, right? Standard conditions, if I measure the delta G at standard conditions, I get the delta G0 prime. Under standard conditions, delta G and delta G0 prime are exactly the same thing. It turns out that delta G0 prime is a constant for a given reaction. Meaning, for a given reaction, A goes to B, the delta G0 prime will always be the same. The delta G will vary. So now if I think about this equation, the delta G for a reaction is equal to a constant plus a log term. Okay, in simple terms, that's what it is. It's a constant plus a log term. All right? If we can understand what's happening with that log term, we're in very good shape for understanding what's happening with delta G. All right? Well, how do we understand what's going on with the log term? This is where everybody wants to get a calculator out and blah, blah, blah. And people get calculators, and they get numbers that make no sense because this equation doesn't have a meaning for them. I want you to be able to do this and to think about this without a calculator. In my 450 class, I don't let students bring a calculator because it makes them think about this equation. Now, I let you bring a calculator, but every problem that I will give you, you will not need a calculator. You will like it because it gives you security. I feel better having it there. And I'll get a few nervous students before each exam saying, you said we could have a calculator, right? Yeah, your security blanket too, okay? You know? But the fact of the matter is, you're not going to need a calculator. I will give you problems that are simple enough to understand that a calculator will be completely meaningless for you. Okay? Well, how does that happen? The log term, understanding what that log term tells us, is really the root of understanding this. My God, I hated logarithms. And you know why you hated logarithms? Because you learned them on a calculator. That's why you hate them? I'm going to show you logarithms in a way you haven't seen logarithms before. Okay? Let's imagine I've got a reaction, A goes to B. Let's imagine I've got 5 times as much B as I've got A. The ratio of B to A would be 5 to 1, correct? What's the logarithm of 5? Where's my calculator? Right? Because you see the logarithm as a number, and it is a number, but that's not the most important thing. The most important thing is that that is a positive number. Logarithm of a number greater than 1 is a positive number. So if I gave you that, 5 times as much B as A, you would say, well, the log term must be positive. All right? You with me? If I told you that the delta G0 prime for a reaction was 0, and there was 5 times as much B as A, what would you say about the delta G value? The delta G value has to be positive, right? Because the log term is positive, and the delta G0 prime in this case is 0. 0 plus a positive number is always going to be a positive number. So which direction is that reaction going to go? Backwards, right? Did you need a calculator? No! Right? If the value of the log term is less than 1, the log term is a negative number. The value of a log term is less than 1, the log term is a negative number. So instead of, let's say, instead of 5 over 1, it's 1 over 5. That's less than 1. That's 1/5. That log term will be negative. Given what I just told you, what would you say about the direction of the reaction? Forwards, right? No calculator. Clear as mud, right? Everybody's with me. Understand? Does that seem like it's difficult? If the ratio of A to B is 1, the log term has a great value, 0. If the number in the parentheses is equal to 1, the log term is equal to 0. Now, I told you a minute ago, or a couple minutes ago, that the delta G0 prime was the delta G under standard conditions, right? Under standard conditions, I have equal amounts of A and B. What's the value of the log term? The value of the log term will be 0. Therefore, delta G equals delta G0 prime, and that's what I told you, that you accepted, and now you know why. Everybody following? Let's do a harder one. Let's imagine I told you that the delta G0 prime for a reaction was positive 4. Okay? Positive 4. And I told you that the reaction was going forwards. What does that tell you about the delta G0? What does that tell you about the delta G? What does that tell you about the ratio of B to A? Do you have more A or do you have more B? Okay, so let's step through it. Delta G value is negative. Means that those two numbers added together have got to be a negative number, right? The first one's a positive number, which means that the log term has got to be a negative number, right? To make it a negative number, do I need to have more A or more B? More A, right? B over A. Got to have a smaller and smaller number, right? You can do that. No calculator. In fact, if I gave you that on a test, you wouldn't know what to plug into the calculator because I didn't give you a number. Right? Oh my God. This is what I like to call practical mathematics, okay? We spent so much time teaching people to punch numbers in that they don't even understand in the first place, that when they get one of these things, they go, oh my God, I've got to do a logarithm. Because they didn't understand what a logarithm was all about. This is what logarithms are useful for. You guys with me? If you work through some of the practice problems I have on the schedule page, you'll get a better understanding of some of these things. Okay? Some of them will let you use a calculator. Some of them you won't need a calculator for at all. Work through those. If you don't understand them, if you want additional help, come see me. I'll be more than happy to help you. Okay? If you want a tutor or something like that, I'm also happy to help you. And I've got TAs that are more than happy to help you as well. Okay? So, questions before I move on? Everybody's got logarithms figured out. Why didn't they teach you this as freshmen? I don't understand. Okay? Did you guys do Henderson-Hasselbalch with Dr. McFadden? Same principle. What is Henderson-Hasselbalch? pH equals pKa plus log of salt over acid, right? pKa is a constant for any given acid. Okay? The log term and a constant. Does it sound familiar? pH is equal to a constant plus a log term. Oh yeah, it makes sense. Okay? You can work every problem with that. As long as they're not asking you for a specific number, you can work every problem with those without a calculator. That's a really powerful thing. Very, very powerful. As I said, I will let you have a calculator, but you're not going to need it. Okay. So move on. Anything you want to ask? I see at least a few people smiling. That's good. So, all right. So let's start talking about something that students tend to like a lot. And I'll tell you why they tend to like it a lot. A, they've typically had it. Oh, yes, I remember that stuff. Okay? And number two, it's very basic memory. Okay? Very basic memory. Not a lot of difficult concepts in what I'm getting ready to show you. You had a lot of this in organic chemistry. So a lot of what I'm going to tell you here is review. All right? Carbohydrates. First of all, let's talk about the word, carbohydrate. Carbohydrate literally means carbon water. Carbon water. Okay? This arises from the fact that if we look at the formulas of carbohydrates, at least the simple ones, they have the following form. CX, where X is a number, H2O, also with an X. Carbon water. So for glucose, for example, we have C6H12O6. I could write that as C6H2O6. Carbon water. Okay? So carbohydrates are carbon water. We also call them sugars, and we also call them saccharides. A lot of similar names. We call them a monosaccharide if they're a simple sugar, and we have less simple sugars that we'll talk about as well. The word saccharide literally means sweet taste. Saccharide means sweet taste. Okay. A lot of nomenclature, okay, associated with carbohydrates. So I'm going to step you through the nomenclature fairly quickly because I think you've had this in organic chemistry. Okay? Carbons can have 1, 2, 3, 4, 5, 6, 7, or 8 sugars and be what we call a monosaccharide, a simple sugar. Generally, we talk about the simplest sugars as having 3, but technically they can actually have 1 or 2. We won't work with 1s or 2s. Okay? The simplest sugar we will talk about is what's called a triose. And by the way, whenever you see the letters OSE at the end of a biochemical name, that's referring to a sugar of some sort. A triose, tri means 3, means a 3-carbon sugar. A tetrose means a 4-carbon sugar. A pentose is a 5-carbon sugar. A hexose is a 6-carbon sugar. 7 is actually called a septose, although we hardly ever refer to them. Okay? Or a heptose. Either one's acceptable. And an octose has 8. Okay? When we look at sugars, we discover that they come in 2 different chemical forms. One form is known as an aldehyde, and you learned aldehydes in organic chemistry because that meant it had a double bond oxygen on the terminal carbon. A good example of that is glyceraldehyde that you can see right here. And there's that double bond oxygen on the terminal carbon. You'll notice that all the other carbons, in this case both the other carbons, have hydroxyl groups on them. So one kind of carbohydrate, or one kind of sugar in this case, right? One kind of sugar is an aldehyde, and an aldehyde sugar has the name of an aldose, A-L-D-O-S-E. The other chemical form of sugar that we have has a ketone. You can see a good example here, hydroxyacetone. Okay? I'm sorry, dihydroxyacetone. Sorry, not hydroxyacetone, dihydroxyacetone. Dihydroxyacetone has a ketone group, and as you might guess, we call these ketoses. Okay? These guys, by the way, have exactly the same formula, C3H6O3. Just different form, but they have exactly the same formula in terms of number of carbons, hydrogens, and oxygens. Okay. On the left is the most common sugar on the face of the earth. It's glucose. There are very few structures I require you to memorize in this class, but this is one of them because you're going to need it in other classes. On the left, you see glucose in what we call the straight chain form. It's what I call the Fischer form, F-I-S-C-H-E-R. We'll later see that there's a ring form of this called the Haworth form. Okay? You need to know the structure of glucose in both the straight chain and in the ring form. That is both the Fischer form and in the Haworth form. You see it in the Fischer form on the left. I memorized glucose when I was in college as the following, okay? It's an aldose, so I see the terminal double bond oxygen. I see hydroxyl on the right, left, right, right. That's how I remembered it. Right, left, right, right. Every carbon in the middle of this sugar is asymmetric, meaning it has 4 different things attached to it. And in 3-dimensional space, there are 2 different ways to attach 4 things to it. Okay? In organic chemistry, you learned about R and S forms and naming and so forth. And I like to say biochemists are lazy people. We don't do that, at least for the sugars. Okay? That saves you some grief. We like to keep it simple. We refer to these guys as D and L. Right? D and L actually works very well for sugars. Because if we look at a sugar like glucose, it's written as you see on the screen. If you look to the next to last carbon from the bottom, excuse me, if the hydroxyl is on the right, that has to be a D sugar. If the hydroxyl is on the left, it has to be an L sugar. You can see that this glucose that's shown on the top is in the D form because the hydroxyl is on the right. And if we look at the ketose fructose, and by the way, that's the most abundant ketose on the face of the earth, we see that it's also in the D configuration. Okay? But we see it has a ketone instead of an aldehyde. Aldehydes, you might remember from organic chemistry, are fairly reactive. Ketones are not nearly so reactive. Okay? That comes into play a little bit later when we talk about things. Every one of these hydroxyls can be on either the left or the right. And that means that there's a lot of possible, what we call stereoisomers of sugars that can exist. Many possible stereoisomers. I'm going to show you several examples. And by the way, fructose is another one that you should know the structure of. Okay? I will tell you all the ones you should know the structure of. Glucose being one, fructose being another. There's only about 4. All right. So, if I get moving around the hydroxyls, all right, I can make, for example, a mirror image of something that I've got up here. Glucose is a good example. I have the hydroxyl on the left. I'm sorry, on the right, left, right, right, right? If I were to want to describe, if I asked you to draw the structure of L-glucose, it would be not just the bottom hydroxyl moved to the left, but every hydroxyl flipped. It would be the mirror image of D-glucose. So L-glucose would be the mirror image of D-glucose, meaning that instead of the hydroxyl at number 2 being on the right, it would be on the left. Instead of the hydroxyl on number 3 being on the left, it would be on the right, etc. down here. L-glucose is the mirror image of D-glucose. Well, if we get adding these up, there's 2 possible positions for this hydroxyl. There's 2 possible positions for this. There's 2 possible positions for this. And there's 2 possible positions for this. That means we've got 2 to the 4th possible different aldohexoses or aldoses. By the way, I said an aldose, right? So I could describe this guy as an aldohexose because a hexose was 6 carbons, aldehyde being an aldose something. Or I could call it a hexoaldose. I don't care. Okay? But suffice it to say, we would have 16 possible ones of these. How many possible ones of these would we have? Well, in this case, carbon number 2 is not an asymmetric carbon, so there's only 3. 1, 2, 3. So we would have 8, that is 2 to the 3rd, 8 possible different ketohexoses. Okay. Here's a simple example, all right? Here's a 4-carbon sugar, known as erythrose, on the left, or threose on the right. All right? Erythrose and threose are what we describe as stereoisomers of each other. Right? They're not mirror images. They're stereoisomers. And stereoisomers that are not mirror images are called diastereomers. D-I-A-S-T-E-R-E-O-M as in Mike, E-R-S. D-I-A-S-T-E-R-E-O-M-E-R-S. I'm going to repeat what that is. Diastereomers are stereoisomers that are not mirror images of each other. If I have stereoisomers that are mirror images of each other, like D-glucose and L-glucose, stereoisomers that are mirror images of each other are called enantiomers. E-N-A-N-T-I-O-M-E-R-S. E-N-A-N-T-I-O-M-E-R-S. Enantiomers are stereoisomers that are mirror images of each other. Let's look at this up here. D-erythrose and L-erythrose are enantiomers. D-erythrose, D-threose are diastereomers. D-threose and L-threose are enantiomers. Right? Mirror images. Okay? In fact, whenever you see D and L followed by the same name, they will always be enantiomers. D and L glucose are enantiomers. D and L fructose are enantiomers. D and L ribose, as we will see, are enantiomers, etc., etc. There's no structures up here you need to memorize. None. Okay? All right. This shows, okay, the D isomers, starting with 3 carbons, 4 carbons, 5 carbons, 6 carbons. And you said, but Kevin, wait, there are 16 6-carbon ones. This is only showing the Ds. Okay? Only showing the Ds, for which there are 8. 1, 2, 3, 4, 5, 6, 7, 8. We will also have 8 L isomers. Of the ones up here, there's only 3 I'm going to ask you to memorize the structure. Glucose. I'm sorry, there's only 2 up here. One other one later, okay? 2 here, glucose and ribose. And ribose turns out to be the easiest pentose for you to memorize. You've actually seen it already because ribose is found in ribonucleotides. It's really simple in the straight chain form. First of all, it's an aldose, meaning it's got an aldehyde group. Second of all, look where all the hydroxyls are. They're on the right side. It's very, very simple. If I said, what's the structure of L-ribose? I hope that you would say, well, the D had them all on the right side. The L must be the mirror image, which must mean that all the hydroxyls would be on the left side. Very, very simple one to memorize. The 3 sugars I want you to know the structures of, ring and straight chain, are glucose, fructose, and ribose. That's it. Glucose, fructose, and ribose. And I make you learn those because you will need them in other classes. I don't believe in making you memorize something for the sake of memorizing something because that's just a waste of your time. But you will need these in other classes. So if you memorize them here, they'll be much easier for you to remember when you have them in other classes. Well, I said that we also get ring structures for these sugars. Okay? Sugars that are 5 or 6 carbons long can fairly easily form ring structures that are either 5 or 6 membered rings. This shows the formation of the ring structure of glucose. Here's the straight chain form. This shows that carbon number 5 has a hydroxyl group that connects with carbon number 1. So we're connecting carbon number 1 and the hydroxyl group of carbon number 5. That gives us something that looks like this. Okay? Now let's count the carbons here. Carbon number 1, carbon number 2, 3, 4, 5, and notice that number 6 is not in the ring. It's above the ring. Okay? Whenever you see or you think about a ring structure, I always want you to count the carbons. It will always keep you out of trouble. Okay? Count the carbons. Number them. 1, 2, 3, 4, 5, 6. Well, forming the ring actually created a new asymmetric carbon where 1 did not exist before. Carbon number 1 in the ring structure is asymmetric because it has 4 different things attached to it, which means now the hydroxyl, which is formed by this ring structure, the hydroxyl on carbon number 1, can be in 2 different configurations. It can be in the down configuration, in which case we call it alpha, or it can be in the up configuration, in which case we call it beta. There's still more nomenclature. You'll notice that this is described on the top one as alpha-D glucopyranose. What's a pyranose? A pyranose is a sugar that has a 6-membered ring. Okay? 1, 2, 3, 4, 5, 6. Oxygen is one of the members of the ring. Okay? So a pyranose is a sugar. Whenever you hear the term pyranose, it tells you it's in a ring. And it tells you specifically it's in a 6-membered ring. And yes, glucose can form a 5-membered ring, and no, we're not going to worry about it because it's rare. Glucopyranose we're going to be concerned about. Okay? Now, you'll notice that your book calls Fischer Projections, a lot of people call these Fischer projection formulas, and they draw a sort of a ring. I don't like to use that nomenclature. I like to say that what we actually see on the left is a Fischer. So Fischer is a straight chain versus a ring. The ring is called a Haworth. Okay. If we look at blah, blah, that doesn't do anything. Oh, sorry. If we look at Haworth projections, okay, we see that here is a 6-membered Haworth ring for glucose, It's also possible for things to be in a 5-membered ring, and one of the things that commonly appears in a 5-membered ring, there's two things. One is fructose, and one is ribose. You should know the structures of glucose, fructose, and ribose in straight chain and also in ring form. Okay? Know both of those. All right. In the 5-membered ring, we call these furanoses, F-U-R-A-N. That's actually easy to remember because furan starts with an F just like 5 starts with an F. Furanose has a 5-membered ring. A pyranose has a 6-membered ring. The eyes are getting very heavy. I could hypnotize you guys. Do you realize that? I could just hypnotize you, and everything I say, you would just go like a zombie. Give me your money. Give me your credit cards. You know, after a long lecture, you realize how easy that would be to do? I should try that sometime. How's everybody doing, okay? Questions or thoughts? A lot of nomenclature. Yes? Okay, good question. She asked if you would see a 6-membered ring for ribose or fructose. The answer is you could see a 6-membered ring for either one of those, but again, they're very rare, so we're not going to mess with them. So we'll worry about a 6-membered ring for glucose and 5-membered rings for fructose and ribose. Okay. Other thoughts or questions? Yeah. Very good question. For the alpha and betas, they're a 50-50 split. That actually was something I wasn't going to dive into, but I'll just answer your question, then I'll actually talk about it tomorrow. Okay? There's not a 50-50 split. And the reason is because that when we draw these out with the actual angles that are found in among the carbons, okay, we discover that these things can exist in a couple of different bends that are conformations. All right? And so one of the bends actually brings this guy up, in which case it interferes with this guy here. Because you see this carbon is above the ring. All right? When this bends up, it's in what we call the boat form. In this form, it's the chair form. So it tends to prefer the chair form and the alpha so that the hydroxyl is farther away. That's basically what it tends to prefer to do. Yes? No, not really. You're not going to draw this out like that. But I think you should know, I mean, schematically what a chair looks like. I like to think of a chair as looking like a chase lounge and a boat as if this thing bends up. All right, I think it's about song time. You guys want to do a song? All right. This one I've got a recording of because I don't sing it very well. You guys know the song Penny Lane by the Beatles? Okay, this one's to the tune of Penny Lane. It's called NAD. If it gets started. While they lower Gibbs free energy, thanks to enthalpy. If the substrate is converted from an alcohol to an aldehyde or ketone, it is clear those electrons do not disappear. They just rearrange. Very strange. NAD is in my ears and in my eyes, helping molecules get oxidized with NADPH. And the latter is a problem anaerobically, because accumulations of it muscle state. They respond by using bionucleate to produce lactate. happened here? I've lost my lyrics. Somehow my lyrics got messed up there. But in any event, we're all set. So see you guys tomorrow.